تفضل. ايوه والله عافية. تفضلي والله بس خلينا نخلص درس نشوف تفضل. ماشي.
اوكي. اوكي.
سوري دكتور بيت. السلام عليكم.
السلام عليكم.
جناب دكتور, some of the student has class language variation, okay?
It has not
no.
finished yet?
No, his
exam?
I think, no, not exam. I think he's 5 minutes after his beginning. What's your suggestion about this student?
5 minutes later. 5 minutes later, the language class is starts.
His beginning. Yes.
Oh. Okay. So please save the class. Okay. I thought that the language. If I know, I make the session on another day, but I don't know that there is a class on this time. Okay. Anyway, let us start. Okay. We reached to recovery, to concurrency control chapter. In the previous chapter, we talked about transactions, serializability, recovery, cascading, rollback, and so on. In this chapter, we are talking about concurrency control. Okay, let me write on the whiteboard. Okay. Concurrency control. As I said before, we should control the concurrent execution of transaction. Otherwise, they make a problem. They make inconsistency. So if we would like to have consistent execution of transaction, we should control their execution, because some concurrent schedules may be inconsistent. Okay, so we should only let executions that guarantee consistency. This is the task of DBMS. DBMS should control the execution of transactions. DBMS should control the order of execution of operations of transactions. This is the meaning of concurrency control. There are some ways to control concurrency. One of these ways is approaches that use locks. We say to this approach lock-based approach, or lock-based protocol. Protocols means rules. Okay, rules for the way that we do something. So we say to this approach protocols. Lock-based protocols. Lock-based protocols are the approaches and the algorithms that use locks. When a transaction wants to read or write a data item, it likes that data item first. Okay, so we should talk about likes. We have two types of likes: shared likes and exclusive likes. Exclusive. We have two modes. We have two modes for liking: shared modes and exclusive modes. Okay, or two types: shared and exclusive. If a transaction if a transaction takes a shared like on a data item, then that transaction can read that data item, only can read that data item, but cannot write. Okay, so if a transaction has obtained a shared mode log on item Q, then it can read but cannot write Q, but cannot write Q. So shared mode is just for reading. If a transaction takes a shared mode on a data item Q, it only can read that data item and cannot write. On the other hand, exclusive mode, we have exclusive mode. If a transaction takes an exclusive mode like on a data item Q, then it can read and write. Q. If transaction has obtained an exclusive mode like on item Q, then it can both read and write. Read and write Q. Okay, so if a transaction wants to both read and write the data item, it should take an exclusive mode like, and if he need just reading a data item, it can take only a shared mode like. Okay. We show shared mode like by S and exclusive locks by X. Okay. So we have two lock modes, X and S. Sorry if I think someone would like to enter the class. Okay. Okay. When a transaction wants to read or write a data item, first it should take a lock on that data item. Then it has permission to read or write the data item. So before reading or writing a data item, a transaction should takes a lock on take a lock on that data item. Transaction should request a lock on data item, and if DBMS checks that request and maybe grant that request, or maybe denied the request according to the protocol. So DBMS is responsible for giving or granting locks to transactions, granting lock requests of transactions. So we can draw a picture like this. For example, we have a transaction here. Transaction, for example, TI. Sends lock request to DBMS or lock manager, DBMS, a part of DBMS which is a lock manager. Lock manager. A lock manager checks the request and send the reply or grant the lock request. After transaction sends a lock request to lock manager, the transaction goes to waiting state and do nothing, and should wait until lock manager grants its request. So when a transaction sends a lock request, the transaction waits until the lock manager grants its request. There is a table, or lock manager has a table for these two lock modes. Which shows the consistency of shared and exclusive locks. If a transaction, for example, TI, has a shared lock on a data item, If another transaction TJ wants also a shared log on that data item, it is okay. So two transactions may have shared logs at the same time on one data item, because shared logs only used for reading. More than one transactions can read a data item at the same time. So there is no problem for two transactions have a shared log on a data item at the same time. So we write T or true here that shows consistency between shared modes. So S and S, or two shared modes, are consistent. We put T here. But shared mode logs and exclusive modes are not consistent, so we put false here. Also for X and S we put false. For X and X we put false, because when a transaction takes an exclusive mode, it can read and write that data item, and we cannot permit other transaction to read or write that data item. Exclusive mode logs means that only one transaction can have a log, and if a transaction has an exclusive log on a data item, then no other transaction can have a log on that data item. So only two shared mode logs are consistent, and other logs, like modes, are not consistent. This table is called log compatibility matrix. Log compatibility matrix. Okay. A transaction can send a like request by these operations, like request operations, or like S, for example, on Q, or like X on Q. Like SQ means that a transaction sends a shared mode like request on Q. Like XQ means that a transaction sends an exclusive mode like request on Q. Okay. Okay, let me continue. So transactions should use these like request operations in their code. For example, we have transaction T1, which wants to read and write B, and also read and write A. So because T1 would like to both read and write B, he sends like X request on B. After it gets a grant from like manager, it continue and reads B. Read B and modify B and write B. Now he can release the lock. For releasing the lock, we have unlock operation. Unlock B, release the lock on B. So other transaction can take the lock, because this transaction release here the lock. After that, this transaction wants to read and write data item A, so sends like request X on A, read A, modify A, and writes A. After that, this transaction does not need the lock and can release the lock, so use unlock operation to unlock A. Okay, as you see, we have some operations for locking and for getting locks and for releasing locks. Okay.
Sorry, doctor. This
Yes,
exam
please.
in share mode or in exclusive mode?
Which one?
This example that you have write it in
Because
share.
transaction T1 both
Yes.
reads and write B, it should request an exclusive like,
Exclusive. Yes.
because it wants both to read and write.
Yes, doctor. Yes.
But if a transaction only wants to read a data item, it can only
Should be
request
shared.
shared mode. Okay.
Okay, doctor.
So for writing or for both reading and writing, we need an exclusive mode, like. But only for reading, a shared mode like is enough. We can get a shared mode like on data item. When a transaction takes a shared mode like on a data item, the other transaction also can come and take shared mode like on that data item. But if a transaction takes an exclusive mode like on a data item, then no other transaction can come and takes likes on that data item. Okay.
Okay, doctor.
Also, suppose we have another transaction T2. T2 also T2 transaction just wants to read two data item A and B and display the sum of the amount of these accounts. So just needs a shared mode likes. So T2 send like S, which denotes shared, like S A sends a shared mode like on A to like manager, and after granting the like, it can read A. Then he can unlock A. Then he can send request on B, like S on B. After granting the like, transaction reads B and can unlock B. And then display the sum of A and B, A plus B. Okay, this is another example of transaction that use likes for accessing data items. When system use like-based protocols, any transaction before accessing a data item should request a like on that data item and wait for like manager to grant its request. Before granting that like request, the transaction is in a waiting state and waits until a grant is received from like manager. When like manager grants that request, then transaction can continue and do the following instructions. Okay. Now let's have an example, have an sample schedule of these two transactions. We have these two transactions, and we can have many schedules using these two transactions. A serial schedule T1, T2, a serial schedule T2, T1, and also many concurrent schedules. Suppose let me consider a concurrent schedule which by these two transactions. Consider these schedules. T1, T2, and like manager or concurrency control manager. Concurrency control manager. Concurrency control manager is a part of DBMS which control the concurrency, or we can call it like manager. Okay. First, suppose the first operation of T1, which is like request like X on B. So consider like X on B by T1. This request sends to a concurrency control manager. Concurrency control manager check the request. Okay. Because at the moment, no other transaction has like on B, so there is no problem. We can grant, or like manager can grant this request. grant X on data item B for T1. Okay, grants the request. When this request is granted, then T1 can continue and do the following instructions. Okay, what's the next operation? The next operation is read operation. After granting the like request, read B is executed. So T1 reads B and modify B. B is minus by $50 and write a B, because T1 has an exclusive mode like on B. T1 can read and write B by this exclusive like. After that, T1 unlocks B. When T1 executes unlock B, sends a request to sends a message to concurrency control and says to concurrency control that T1 does not need does not need the lock of B anymore, and so concurrency control can release the lock. Okay, now suppose T2 execute its first instruction, which is lock S A. This request is sent to concurrency control, and there is no lock on A at the moment, and so concurrency control can grant lock S on A for T2. After granting the request, T2 can continue and read A is executed. After that, the next instruction is unlock A. After that, the next instruction is lock S on B. Okay, before T2, T1 has get a lock on B, but here T1 released the lock on B, so at the moment there is no lock on B, and so T2 can get the lock and its request grants. So like manager grant like request like S on B for T2. After that, T2 can continue and read B, and then unlock B, release the lock of B, and display, and runs the display A plus B. Okay. Then the other instructions of T1 is executed. Suppose the next instruction of T1 is lock X A. This request is sent to concurrency control manager. There is no lock on A at the moment because transaction T2 has unlocked the lock of A here. So here, when T1 sends this request, there is no lock, and concurrency control can grant like X on A for T1, and then T1 can continue and read A and modify A. A is plus by 25 and write A, because T1 has exclusive like, it can read and write A. Then unlike A, which sends a message to like manager to release the lock of A. Okay, this schedule is a concurrent schedule and use locking. Okay, the question is that if we use locking, is it enough for consistency of the schedule or not? We have here a concurrent schedule, and this concurrent schedule use locking. Transactions of this schedule use locking for reading shared lock and for writing and reading exclusive locks. But the question is that if we use locking, is it enough to have concurrent execution, to have concurrent schedules that are consistent? Let me check the consistency of this schedule. Sorry. Okay. Okay. Let us start from the first instruction, T1 lock XB, and get the lock on B. Read B. For example, suppose B is 2000, B is 2000, and suppose A is 1000. T1 reads B, B is 2000, B is minus by 50, and B is written. So B on database here is 1950. Then lock of B is released.
السلام عليكم دكتور.
Salaam alaikum.
دكتور.
Okay, salaam alaikum wa rahmatullah. Okay, let me continue. Then like
We
SA.
have looks at Doctor. We have looks X on B on line 9, but we get granted X S on B of T2. This is X or S on looks X of B.
Okay. T1 sends a X like request on B, okay? And concurrency control manager check, and there is no problem, so grants this request for T1. Then T1 can continue and read B, modify B, write B, and release the lock. Okay. Then T2 sends a shared mode like S on A. This request is sent to concurrency control. Concurrency control checks, and there is no problem, so grants this request, this shared mode request on A for T2. So T2 can continue, read A, which is 1000.
وأنا خبرت أخذ
Unlike A, really release a message to like manager. Then T2 sends another request on another shared mode request on B. Here is a shared mode. Okay. Shared mode request on B because transaction T2 only reads A and B, so its request is in shared mode. And concurrency control grants this request for B, grants shared mode like on B for T2. Then T2 continues and reads B, unlike B. What T2 reads is the last value of B on the database, which is 1950. So what it reads, what value it reads is 1950. And when it executes display operation, what is displayed is that A plus B is 1000 plus 1950, which is 2950, which is not equal to 3000. So on the display, user sees that the sum of the amount of accounts is 2950, but it is not okay, because before running this schedule, the sum of the amount of the accounts was 3000, so $50 is missed here, and the situation is not consistent. So as we see, there is an inconsistency here. Despite using liking, we reached to an inconsistent situation, to an inconsistent state. So this example shows that using liking is not enough for consistency. We need other things. We need an additional thing. What's the additional thing? The additional thing is a protocol. We need liking and also a protocol for liking. We cannot get likes and free likes in any order. Should be a rule. We should get like and free likes in a specific manner, in a protocol, according to a protocol by an algorithm. We cannot freely get likes and free likes in any order, at any time. So we should obey some rules. There should be a protocol. So this example shows that just having liking is not enough for consistency. Okay? Any question? Okay.
No, thank you.
But why we reached to an inconsistent situation? This is because because transactions freeze or unlike their likes soon in an improper time. Here T1 takes a lock on B, takes an exclusive lock on B, and here T1 unlikes B. When T1 unlikes B, so T2 can here gets the lock on B and can read B. Okay, so unlocking B lets T2 is executed in the middle of T1. Some parts of T1 is executed, then T2 is executed, then some other parts of T1 is executed. If you see, this schedule is not conflict serializable. Why? Why? Do you know why this schedule is not conflict serializable?
It's not consistent.
Doctor, it's not conflict.
I do not hear your voice is low. This schedule is not conflict serializable. Why?
Because it's not consistency, Victor.
Do you remember in the previous session when an schedule is not conflict serializable and when it is conflict serializable? Do you remember precedence graph?
If we have a cycle, then it's
Yes, exactly.
it's
We
not
have a
conflict.
cycle.
So if we
We have a
don't
cycle.
have, if we don't, yeah.
Okay. Please continue.
So if we have a cycle, then it is not conflict serializable. And if we don't have the cycle, so it's a cyclic, then it's conflict serializable.
Yes, exactly. It's exactly true. Here you see T1 read B and write B. Write B of T1 conflicts with read B of T2, okay? And because write B of T1 is executed before read B of T2 in the precedence graph, we have an edge from T1 to T2 because T1 first writes B and then T2 reads B. So there is an edge between T1 to T2. Again, here we see T2 reads A, okay? And in the following here, T1 writes A. These two operations are conflicting. Read A of T2 first and then write A of T1 because T2 reads A before and T1 writes A after that. There is an edge between T2 to T1. So we have an edge from T2 to T1. So we have a cycle in precedence graph. Precedence graph. Because there is a cycle in the precedence graph, this schedule cannot be conflict serializable, as you can remember from the previous session. So when it is not conflict serializable, if we do not have serializability, we cannot sure about consistency, because the only way that we can show consistency is serializability. But here the schedule is not serializable, is not conflict serializable. And as you saw, we checked the values of A. We reached to this fact that A plus B is not 3000. It's 2950. So this schedule is not consistent. This schedule is not conflict serializable. Okay. So this example shows us that having logs is not enough. We should have an other thing. We should have an additional condition. We should have an additional. We should have some additional rules. We should have a protocol for logging. Okay. How we can avoid this situation, this inconsistent situation? One solution may be that transaction T1 do not unlike B here. Transaction T1 maintain its log until the end of the transaction. So when T1 do not release the log, do not release its logs, so T2 cannot come and execute it between instructions of T1. So this situation cannot occur. So one solution is that T1 and also T2 do not release their log until the end of the transaction. So we can put all the unlocks at the end of the transactions. So I can write the solution here. Sorry. Okay. 1 solution to avoid inconsistency is holding the logs by the transactions until the end of transaction. For example, T1 can be something like this. T1 like X B read B is B minus 15, write B. Then here it does not unlike B, and unlike B at the end. After that, it likes A, read A, modifies A, and writes A. Then at the end, it unlike B and unlike A. Okay, this is a solution, and by this solution, we do not have inconsistency. We do not have schedules that are inconsistent. But it is not good, because if transaction holds larks until the end of the transaction, so the other transaction cannot get their logs, and should wait until the transaction is finished and unlock and free the logs. Okay, so by this solution, we have a low level of concurrency. Concurrency is decreased because transaction holds lock and prevent the other transaction to get their logs, and transactions should wait for other transaction to free the logs, and they do not free the logs until at the end of transaction. So this solution is not so good. We can give another solution. By this solution, we have consistency, but we have low concurrency. Okay, because transaction holds their lock. We need another solution. We need another way which is better and has more concurrency. Okay.
The first unit you need to know. Excuse me.
Okay, any question? Okay, so we need a better way. The better way is a protocol which is called the two-phase locking protocol. We need a better solution. A two-phase locking protocol, which is called 2PL, two-phase locking, 2PL. In brief, 2PL, two-phase locking. Oh, but what is 2PL protocol? 2PL protocol says that transaction each transaction should be divided into two parts. Okay, suppose we have a transaction TI. This transaction should be divided into two parts. If we draw a horizontal line, the first part is the instruction that comes before this horizontal line, and the second part is the instructions of TI that come after this horizontal line. This is phase 1. The first part is phase 1. The second part is phase 2. In the phase 1, transaction can only request locks, and it cannot unlock the locks. It cannot free the locks. So in the first phase, or in phase 1, only transaction takes locks and do not free the locks. In the second part, in the second phase, transaction just free the locks and does not request a new lock, does not take new locks. Okay, so all the locks should be taken in the first phase, and all the unlock should be executed in the second phase. This is the rule of 2PL. 2PL force transaction to be divided into two phases. In the first phase, only transaction should take locks, and in the second phase, transaction should release locks and cannot take a new lock. So here we may have lock, for example, lock X A and some other instructions, then lock XB, then some other instructions, and in the second phase, maybe some instructions, unlock operations, some instructions, again unlock operations, and some instructions. So it is not forced that all unlocks be at the end, but all the unlocks are forced to be in the second phase. We can draw a horizontal line that divides the transaction into two phases, into two parts. In the first part, just we get locks. In the second part, we just release the locks, and we do not get locks. So if we have a transaction TJ, which is something like this, for example, he takes lock A, he read A, modify A, write A, unlock A, then lock X B and something else. It is not this transaction is not 2PL, because it does not obey the rule of 2PL, because after unlock we cannot lock again. All the unlocks should be in the second phase, and all the locks should be in the first phase. But this means that after unlocking, the transaction cannot lock. it is not 2PL, because here TJ unlock A and after that locks B, and this is not permitted, because when a transaction unlock, the unlock should be only in the second phase and locks in the first phase.
On two
First
phase.
phase is called growing phase, and second phase is called shrinking phase. So all the locks should be get in the growing phase, and all the unlocks should be in the shrinking phase. Any question? No question. Okay.
Doctor, please, some of our classmates want to join your
Okay.
team.
So it's an easy protocol. Just says that each transaction should be divided into two parts. In the first part, transaction can lock and cannot unlock. In the second phase, transaction can unlock and cannot lock. Only in the second phase we do not have any lock. In the first phase, we have not any unlock. Okay. If this rule, if this rule is obeyed by transactions and hold, if this condition holds for all the transactions of an schedule, that schedule is guaranteed to be conflict serializable. I means that if we obey 2PL, then our schedules are conflict serializable. This means that using 2PL protocol, we can show conflict serializability. Okay. Let me talk about a concept. We have a concept which is named starvation. Starvation. Starvation means that the transaction cannot get the resources that it needs. In Farsi, starvation means گرسنگی. Means we do not find food for eating. We do not find طعام. Okay. Starvation in Farsi means گرسنگی. And starvation, we have a starvation if there are some transaction cannot get their resources, cannot get data items that they need. This is the meaning of starvation. let me explain starvation by an example. Okay, suppose we have some transactions TI, TJ, TK, TI. Okay, suppose transaction TI, it comes and get a shared mode like on A, and read A. Okay, suppose a transaction J comes and sends a like request X on A. Like manager cannot cannot grant this request because at the moment TI has a shared lock on A and cannot grant X mode lock of TJ on A because X and S is not compatible when a transaction has an S mode like on data item A. The other transaction cannot get X like on A, but can get S like on A. 2 S like is permitted, but an S and an X is not permitted, or 2X are not permitted. So this request is not granted, and TJ waits because its request cannot be granted because the lock is at the hands of TI, and TJ should wait until TI releases the lock. Okay. Okay. Suppose we have another transaction TK. TK comes here and requests like S on A. Okay, because TK wants a shared mode like on A. Shared mode, 2 shared modes are compatible. So TI has an S mode like on A. TK wants also an S mode like on A. There is no problem. These 2 locks are compatible, and this lock is granted, and TK can get the logs and read A. No, suppose that TI do not need anymore the lock and unlock A. Unlock A. Okay. TJ waits for TI to release the lock. Here TI releases the lock, but still TJ cannot get the lock because there is another lock on A by TK. So again, TJ cannot get its lock and should wait for TK. Again, suppose there is another transaction, for example TR, and here TR comes and like SA. Again, this lock S is compatible with the previous lock S and is granted, and TR can get the lock and can read A. Suppose after that TK unlike A. Okay, again TJ cannot get the like because at the moment TR has another like on A. Even TK release the like, there is another like on A by TR. So again, TJ cannot get the like and should wait. And this scenario can continue forever, and other transaction can come and repeat this scenario. So here TJ for TJ we have an starvation because TJ cannot get the data item, cannot get a like on the data item that it needs because the others have likes on that data item, and we can plan a scenario that forever TJ cannot get its like. This is called a starvation. We have a starvation if we can plan a scenario in which a transaction cannot get its lock, cannot get its data item. Okay, as you see, we may have a starvation by locking because shared lock are compatible and exclusive lock is incompatible with the other locks. How we can prevent starvation? Can you suggest a solution to prevent starvation?
Sorry, doctor.
Yes, please.
Can I ask a question, please?
Please.
Sorry. When TI unlock A, why TJ not get the lock for A? Just for its take lock X A exclusive?
Yes, because TJ needs exclusive lock. Two transaction. If two transaction wants shared mode locks, there is no problem. Two transaction can take two shared mode lock at the same time. But if one transaction wants a lock in an exclusive mode, so no other transaction can get a lock, and there is incompatibility between exclusive lock and the other lock. If TJ wants like S, there is no problem, but because TJ wants like X, it cannot get this lock because at the moment TI has a lock on A in share mode. Okay, as you see here in the compatibility matrix, let me go to the compatibility matrix. This is the compatibility matrix, like compatibility matrix. Sorry. Okay. This is the compatibility matrix, like compatibility. This matrix says that S mode and S mode is compatible. We have true here. But S mode and X mode is not compatible. Also, X mode and S mode is not compatible. X mode and X mode is also incompatible. This means that two transactions cannot have X mode log on a data item at the same time. Also, two transactions cannot have S mode like and X mode like. If one transaction has S mode and the other transaction wants X mode, it is not permitted. The only permitted case is when the transaction has S mode like and the other transaction also wants S mode. Only S mode likes are compatible with each other.
Thank you, Doctor.
You are welcome. Okay, let me continue. So when we use liking, we may have starvation. This means that we may have situation in which one transaction cannot get its needed data item forever. We have other transaction and comes and gets like S on A, and TJ should wait for all of them to release the lock, and this scenario can continue forever and TJ cannot get its lock. How we can avoid starvation? One way to avoid starvation is
Yes, Doctor. By using first come first saved.
Yes, by using a queue.
Queue, yeah.
We can have a queue when because transaction TJ comes before TK and TR, so the priority is by TJ. Because TJ comes sooner than TK. We can have a queue and put the requests in the queue and process them in a FIFO manner. So to avoid starvation, we can use queue. Queue is FIFO data structure. As you have read in the Al-Khwarizmiyat, yes, FIFO, first in first out. This is a data structure. We put the request in this structure. The request is comes first, is served first. So TI gets lock, then TJ cannot get lock because TI does not release the lock and should wait. And this request this request goes to queue, the queue. Then TK comes, and this request is also goes to the queue. And when the lock is released, we process the requests in a FIFO manner. We first get the lock to TJ, and when it releases the lock, then we get the lock. We give the lock to TK in a FIFO manner. So we can prevent starvation by using Q and 5. Okay, I think it's enough for this session. If you have any question, please ask me. No question?
Thank you, Doctor.
Thank you, Doctor,
Thank
so
you.
much.